Well, I think I could start an introduction. We have Nick Graf here today, and I think a lot of people know him. He has degrees in geography and certificates GIST or GIS from University of Wyoming and from Kansas State. Little apple. He worked for a while. Let me see. Originally,
It's 4 years with Kansas Department of Emergency Management.
and then here at YGISC, and now as a YDOT, Wyoming Department of Transportation. And I ran into him at LCCC GIS Day, and he was explaining this new algorithm method they were using for helping with closures on our windy highways, and it just was really, really spectacularly fascinating to me. So I thought, you need to come over here and give this talk. So we're very excited to have Nick Graf let us know what's going on with blowovers on the interstates in Wyoming and beyond.
Well, thank you.
Yeah, thank you very much.
All right, so I'm Nick Graf. I'm one of the GIS supervisor at YDOT. So my goal here is to just go over kind of a novel thing that we've done in the last year to address blowovers, mostly along the interstates, but eventually we'll expand this to be a little bit wider. So why are blowovers, why are we concerned about this? You can see from this chart that the blowovers are increasing with the exception of 2023, which is preliminary data, and we did implement this closure right before the peak blowover season. So that one may be anonymously low, but you can see prior to that, when we started this, blowovers were increasing, and blowovers are a significant problem. So let's talk about why blowovers are increasing. So we have some environmental factors like wind speeds, the wind frequency, the location of the wind events. We have just environmental change. We have drivers, we have changes in how transportation models things. We have things like just-in-time delivery. You guys all saw that during COVID when there was no supplies. Like we have no margins left in our warehouses and all that. So there's incentives for the drivers to get from A to B on time and quickly. We have some complacency from National Weather Service and whatnot. Maybe we've been a little lax on what we consider when closures are enforcing those. The vehicles themselves have changed, and for mostly good reasons. They've gotten lighter, they've gotten more fuel efficient, but with that, they're not as strong. And so consequently, when that vehicle pulls over, the likelihood of it spilling its cargo all over the road is increased, and that closes the road for longer. Or even that trailer, even if it's empty, cleaning up multiple pieces, it results in the interstate being closed for a longer period of time. So while the fuel savings is great, it does have some unintended consequences. And then also there's just changes in Wyoming in general. So Cheyenne has gotten some new distribution centers, which means that there's trucks that are returning empty to those distribution centers to be filled. And it's the light trucks that are more susceptible, and we'll go into that in more details. So what vehicles blow over? What's the definition of a light, high-profile vehicle? So historically, you guys have probably seen the signs. Wyoming has said this road is closed to light, high-profile vehicles. Well, what's a light, high-profile vehicle? If I asked Jason, he'd probably give me a different answer than if I asked Ramesh. Like, what is light, high-profile? It's kind of an ambiguous term. And so a lot of what we've been focusing on is taking a lot of that ambiguity out and clearly defining what vehicles this affects. Sorry to pick on you, Jason. So just a quick timeline. So this all started in May 2023 when the Joint Transportation Commission was critical of the I-80 issues and how long the interstate was being closed and what was going on. So in July 2023, the executive staff at YDOT got a blowover briefing of some research that was done right here at the University of Wyoming by Dr. O'Hara, and he's with the engineering department. Later on in July, there was the first meeting with the executive staff within YDOT. They're in August, so moving fairly quickly, got some buy-in from the Wyoming Truckers Association, so that's an important move. Near the end of August, there was a presentation to the Joint Transportation Committee with a proposed solution. And in October 2023, 23, we had our first weight-based wind closure. So this is the first time we've gone from light, high-profile vehicle to vehicles under 40,000 pounds, for example, gross vehicle weight. So a shift in kind of how we're labeling the closure to remove some of that ambiguity. Yeah.
Sorry to interrupt, but just for clarification on that point, is that like per a certain number of axles? Because like passenger cars aren't included, right?
Correct. So it's it's still high profile vehicles. So
Okay.
we're focusing on, you know, vehicles that are fairly tall. The number of axles isn't as much driven into it. The modeling, which I'll get into a little bit more, is very much based on the combination commercial vehicle, which is kind of what you see here with the 53-foot enclosed trailer. It's really where the research is coming from. But it can be, you know, applied to other vehicles with similar kind of shape and configuration.
Like an RV, a motor coach?
But it's still kind of up to the driver to be like, yes, I am high profile, or no, I'm not.
Yes and no. You know, if it's over a certain height, there's some things, and
Obviously, the truckers know, but
Right.
there's
Yeah.
like some gray area maybe.
right, so we're, you know, very focused on, you know, the commercial traffic.
Okay.
For
Thanks.
sure.
Sorry to interrupt.
No, and those are all great questions. And I'll plan to hopefully address some of
In
those.
theory, could a non-commercial vehicle that's still high profile fall afoul of like if, say, they decide to drive on the road and get blown over, could they still fall afoul of the new rules?
I'm not gonna speak about what the highway patrol would ticket them for, but potentially based on the language of the bill that just passed. But yeah, we'll go.
I have family that has a pretty big trailer.
Yeah.
That they haul around, so.
And we have had several of those blow over. I mean, not probably their trailer, but we've had several blowovers that are not commercial vehicles.
Right.
So, for sure. So let's talk about some of the factors that are driving these blowovers. So you have some kind of static factors like the weight of the vehicle, the center of mass, various things along those lines. You can see that. But we have some variables that are, I would call them spatial variables. So we have the angle of the roadway, and I'll show that in just a minute. We also have the roughness of the height, the relative road elevation, and the altimeter height above the road. So these are all variables that vary over space. Not necessarily over time. The vehicle doesn't necessarily change weights as it's going down the road, but the angle of the road might change. So this is kind of a quick summary of Dr. O'Hara's research. And this is looking, so you can see the truck here. This is along Wyo Hill, which is just outside of Cheyenne. And one of the things that was readily identified was that this, what's called the super elevation, or in that previous slide, the cant angle, plays a big factor. So you can imagine that I've got my little purple angle here, and the wind is coming from that vehicle. So that vehicle, let's say that's 5-10 degrees, somewhere in there. It's a curve, so it's probably 5 or 6 degrees. So that's already, that shifts that center of mass over it. So it doesn't take as strong of a wind to blow that truck over. And so that the super elevation is a really critical thing for us to look at, and the orientation of the road. So just some more summaries of his research. I don't expect you to ingest this entire table. What I want you to see is that on the left side is super elevation. As it increases, the probability of blowover increases as well. And then along the top is the speed of the wind. And so a low super elevation and a low wind speed, it's very unlikely. At a high super elevation and high wind speed, the likelihood is much higher. So that's kind of the take home here. If we increase the weight from 25,000 pounds gross vehicle weight to 35,000 pounds, you can see that where the red zone is has shifted. And so as the vehicle increases in weight, the likelihood of it blowing over decreases.
Nick,
Yes.
on that slide. Is the vehicle speed matters at all, or
It does. Yes.
does it matter?
It matters, and these are, I don't remember what these are, but when for the numbers that I am using for our static table, we're using 75 miles an hour. That's globally the speed limit. But yes, the speed of the vehicle does matter. So that's a fantastic observation. So The other thing that matters is what direction the wind's coming from. So you can imagine if it's a headwind, that truck is gonna be a little bit more stable. If the wind is coming from a cross section or a direct cross section or a slight headwind, that's the most significant. So in this slide, at 30 miles an hour, it has to be pretty much right on and there's not a lot of variability. And this is based on a 30,000 pound vehicle. But if the wind increases to, let's say 40 miles an hour, we've now increased the cones on either side by 60 degrees. And so you can imagine that that is gonna keep increasing. At 44 miles an hour, we've increased that northbound and that southbound cone by 90 degrees. So at 44 miles an hour for 30,000 pounds, the wind direction is no longer a factor. It's the wind speed that's driving. So let's look at what that looks like on the landscape. So this is an area along Elk Mountain. So this is modeling an unrealistic 10,000 pound vehicle. And so you can see here, we have a base wind, our model starts at 20 miles an hour. And we have kind of our base cone at an increase of 24 miles an hour. Those angles have increased significantly. So we're almost at 90 degrees. At 26 miles an hour, so it goes in 2 mile an hour increments, we've passed 90 degrees. So we've hit that 90 degrees plus the variation in the road surface. So for 10,000 pounds, 26 miles an hour, the wind direction is no longer relevant for this particular site. That vehicle is within our risk threshold. So now let's do the same thing, but let's look at 45,000 pounds. So everything else is the same. All we've changed is the weight of the vehicle. So you can see at 20 miles an hour, even at 46 miles an hour, it has to be at a true 90-degree angle for it to really be of concern. Yeah. At 48, that's when we start adding degrees of increments. And we're going to increase that. So at 50, you can see that cone is increasing. So just like that slide I was showing you, this is just a little bit more visual. We're going to keep going. I missed in this one. So at 50 miles an hour, this wind is now in our critical direction. And we're going to keep increasing this. So, it's adding degrees onto that cone of criticality right up until we get to 68 miles an hour. And then that's for 45,000 pounds. That's when you've got to that 90-degree increment. And since we have some variation in the road, it's past 90 degrees and the wind is no longer relevant. So how do we take this research and how do we turn it into something that YDOT can implement? So we came up with 6 easy steps, so to speak. So the first one is identify the roadway characteristics. So we're talking super elevation and the direction of travel. Next, summarize that data for each of our weather stations. Develop tables. So these are wind, weight, direction tables for each one of those weather stations, and I'll go through what those look like. Link those tables to the real-time wind speed and direction. And then provide real-time information to our decision makers. So that's our transportation management center. And then finally, get that information to the public. So totally 6 easy steps, I promise. So each one of these, as you can imagine, is a little bit harder. So identifying the roadway characteristics. So first thing we did is we looked at 5 years of crash data. So you can see in this map, we've got the little orange dots are crashes. Then we compared that to our weather stations. And if there was a weather station that didn't have a lot of crash data, we supplemented that with samples every 10th mile from that weather station, plus or minus 2 miles. So each one of these colors is a different one of our weather stations. So you can see, we're associating roadway characteristics with the weather stations nearby. And the characteristics that we're really focusing on is super elevation that I showed you, that angle of the roadway, and then the direction of travel. So and those are kind of our 2 critical things that we're looking at. So how do we get that super elevation? How do we know what the slope of the road is? Well, turns out YDOT had contracted with a company called Cyclomedia, and they drove our roads to create a product that they call Street Smart. I'm not here to plug Cyclomedia. The important thing is when they drove it, they had side scan LiDAR. I now have LiDAR for our entire road network. So, so I can use that LiDAR, you can see here, to measure across the roadway. And it gives me this slope percentage. So now I know for this particular crash, that super elevation is 5.6%. So I can take that data and I can tie it to our crash data. So now we've got our roadway characteristics. We need to summarize that for each one of our weather stations. So I have a weather station here in the middle of the screen, and I have the, right now I'm showing the direction of travel in here. So you can see that this line corresponds really well to crashes along that particular stretch of road. And this line corresponds to this stretch of road. So we're taking the roadway characteristics of the road within plus or minus 2 miles of that weather station, and we're kind of creating worst case scenario for that particular weather station. Because we don't really care what the weather at the weather station is. We care about what the weather at the worst case nearby road condition is. So we can do that. Once we have the direction of travel, we can now do some things like calculate that critical cone. So we have our azimuth of travel, which is the orange cones. Turn that 90 degrees to get our first critical angle. And then just to keep things simple, I used 15-degree increments for the wind. So I'm going to round the lower angle down to the nearest 15 degree and the higher angle up to the nearest 15 degrees. So I'm increasing that critical cone till it meets our 15-degree increments. And that's, where you saw these little charts. That's where that comes from, is developing those critical cones based on the variation of the road within that weather station. So that enabled me to build this super cool wind weight direction table. So now we've got, going down the left side, we have the wind direction. You can see in 15-degree increments. I don't expect you to be able to read this, but they're going in 15-degree increments. Across the top, we have the wind speed going in 2 mile an hour increments. So let's just, and so we'll do that, and we repeat that for each weather station. So we've got 70 some odd, so just a small sample weather station. So you can see each one of those looks a little bit different. So how do we link then? How do we link the real-time weather data? So we have weather data coming into our database, so we can do that. So in this particular example, let's say that the wind direction is 45 miles an hour. So I'm gonna, in the database, I'm gonna read the 100, or coming from 140 degrees, sorry. So I'm gonna read the 135-degree line and the 150-degree line, because it comes right in between those. So I'm gonna read both above and below to get the worst case scenario. The wind speed is 43 miles an hour. So we have 40, 42, and 44. So where are we going to put 43? So for a factor of safety, anything that's above 42, even if it's a tenth of a mile an hour, gets rounded up to 44. So we read that column. So now we've got 35,000 pounds, 35,000 pounds. Oh, our wind gusts are 68 miles an hour. So do we just read the 68 mile an hour? So it turns out that when Dr. O'Hara did the research, his model was based on, these outputs are based on the wind gust being 150% of the sustained winds. So that's a simple mathematical equation. We can take the inverse of that. We can take 2/3 of the wind gust and treat that as a sustained wind. So in this case, 45.3, that gets rounded up to 46. And now we've got our little box of 4 values. So 35,000 pounds, 35,000 pounds, 40,000 pounds, and 35,000 pounds. So we report the maximum of those is 40,000 pounds. So for these conditions, the minimum weight that the vehicle could have for a light high-profile vehicle is 45,000 pounds gross vehicle weight to be within our things. So I've done that for all of our weather stations along the interstates, and you can see it varies. So this one's at 40,000 pounds, 25. Like there's quite a bit of variability based on the wind speed and the wind direction at that particular site. And so what we want to do is look at that as a holistic picture and get an idea of what we need for that section. So the next step is to get this into the hand of our decision makers. And right now the decision makers is our transportation management center. This is a big It looks like a dispatch room in the basement of a building in Cheyenne, and it's they're the ones that actually close the roads. They're the ones that post messages on the signs. They're the ones that have the power to do this sort of stuff. So we have an internal tool called our TMC Live Map, and so we've incorporated that. And so one of our developers, Ben Saunders, put this together, and it's showing the wind speed, the wind direction, and the minimum weight for that particular stretch. Also, you guys probably can't pick it out, but there's a few here that have an asterisk on them. And so if they have an asterisk, that means that that's the controlling R widths for that particular stretch. So if you're looking at that whole stretch, that to get from Laramie to Rollins, you need 45,000 pounds. So there's some stretches that you can get away with less than that, but you're not going to get all the way to Rollins. So that stretch, we would say 45,000 pounds. Our TMC also can get some track messages. And so track is just kind of an interactive feed about what's going on. So crashes, changes in conditions, that sort of stuff. These are just notifications to that transportation management center. So one track message we might say is add. So if we see this and we see, oh, this stretch, we're saying the minimum weight is 45,000 pounds. There's not currently a weight-based closure on that stretch. We need to add a weight-based closure. So this message tells you to add a weight-based closure from Laramie to Cheyenne based on one particular RWIS with a minimum weight of 40,000 pounds. If there is a weight-based closure, but the wind is now going faster than when it was set up, we might need to increase that. So another message they might receive is increase. So you can see in this one, very similar thing, but we're saying we need to increase it from 40,000 pounds to 45,000 pounds. Another, as conditions improve, and these conditions, so this map here is based on the worst case scenario of the last 15 minutes. So, so it does eventually, as the wind calms down, improve. So in this particular case, maybe the restrictions were 55,000 pounds. The wind has improved. Now we need to drop it to 40,000 pounds. And you can see it's not a one-to-one relationship. If there's more than one RWIS, just like we saw on that map where there was 2 with asterisks, it's going to report all of those as well. And the last one is remove. So if the weight restrictions are below 40,000 pounds, we would just remove the weight-based closure altogether. So some pretty cool ability with the database and the wind speeds to just use database processes to spit out some outputs for our decision makers and just kind of make their lives easier. So how do we get that out to the traveling public? So we have a couple of things already in place. We have our commercial vehicle operators portal where we can get this information out. We have roadside systems. You guys have probably noticed on the messages overhead that those have changed, and they now include things like enclosed trailers or high profile vehicles under 40,000 pounds or under 50,000 pounds. So that's one thing that we can do. We also, Wyoming was part of a pilot project for connected vehicles. So we can get that out to our roadside reporting units and get that into the cabs of trucks and other private vehicles that have these in-vehicle systems. We updated our signage. So you now see that Cheyenne to Douglas is closed to enclosed trailers. It's now just high profile vehicles under 35,000 gross vehicle weight, and gives you some information, crosswinds, various things. Where do we go from here? So some things to incorporate. So we have our Wyoming authorized travel program. We could build something very similar for wind-based events. So your example with your parents in their trailer, we could develop a portal, and I'll talk about that in the next slide, where they could enter some information and kind of get a yay or a nay. Incorporate this into our 511 systems. So the phone, the mobile app, and the notifications all, and that's largely happened. We've incorporated in something that's called the situational data exchange. That's a product by Tri-Hydro right here in Laramie that was developed through that connected vehicle project. And
That's where my books work.
yeah. So that actually gets the messages out to those roadside reporting units and can get those into the connected vehicles. They also have a web interface for people. We have various social media platforms, and then again, that commercial vehicle operating portal. This self-evaluation. So allow people to enter their specific vehicle information, the weight, the measures, some vehicle identification information like a US DOT number or license plate or something like that. And then we can check that against the current conditions and against forecasted conditions and kind of give a yay or nay. So this is kind of the next step in our development process. Another step is just we're never happy. We have the system and we want to be able to continually improve that. So we want to take the system and right now we're evaluating it. It's a shiny new system. We don't know exactly what its capabilities are going to be. So we're kind of in that evaluation stage. Next, we'll move to identifying improvements that need to be made. So, I'm just guessing off the top of my head, but I, mentioned that I used 15-degree increments. Maybe that's too coarse. Maybe we need to use 5-degree increments, or maybe 15 degrees is too tight, and we're sending notifications every 15 minutes, and we need to increase those to 30 degrees. Or maybe we need to, instead of 15 minutes, we look at 30 minutes. Like there's some things that we can change in here. There's also a spatial variable that we can change, that height of the road. We can take that more into effect. We could, update our models to better reflect even more roadside conditions. And results so far have been fairly positive. So we've had 25 blowovers or rollovers, one of which is in an area that we hadn't identified. We've had 2 blowovers in this particular area, one last year and one this year, where the conditions just do not support rollover as far as what our system is saying. So how do we address that? We have 15 of those blowovers are explained by the model, 7 of which might be in that rollover category. We're not entirely sure. This is, very preliminary data. This is brand new stuff. Also, another change is proposed legislation. So currently, a blowover can have a $750 fine and or up to 30 days in jail. There's a bill that would propose for the first offense. The fine is increased to $1,000, still 30 days in jail as an option. But with the second offense, if there's a second offense within 3 years of the first one, the fine is increased significantly. And also it carries with it a reckless driving charge. And so for commercial operators, that's revocation of their license. So that's a significant stick. Yes.
Real quick, is that an actual incident, or is it if they get caught out there?
It would be if they blow over.
But not just.
And they're under the weights, like they're ignoring the closures, they're under the minimum weights and they have blown over, they could be cited, yeah.
Those 15 ones on the previous slide, were those violations?
The 15,
Explained by the
they
model?
would be, yeah, they would be violations. I don't think this legislation is just, in fact, I'll go to the last thing. It just passed, like the governor signed it on March 15th. So this is still very new. It hasn't, I think it goes into effect July 1st, like most of the bills. But it's Senate File 113 if you're really gunning for some reading. But yeah, so they would be potentially ticketed.
Is there any point to include trucking companies in the violations and as opposed to just the drivers? I'm
not as familiar. I mean, that's kind of outside of my purview. I don't know.
You may want to repeat the question for those who are in Zoom.
Okay.
They may not
No,
hear.
they can hear it.
Okay.
Oh, they can. Oh,
Yeah, it's your question?
No, I was just saying in reference to what he was saying. I do actually hold a commercial driver's license, it's Class B, so it's not like a big rig, but my understanding with that is that it would be if they went out and they got and they ended up blowing over, that would be on the driver. But if the driver makes a decision based on the information by YDOT and they get penalized by the company, they can then report that to the Department of Transportation. There can be significant penalties for that company.
Good to know. Yeah, that's the end of my what I've got for slides. I love to entertain some questions, some more questions, I guess. Yeah, Ramesh.
So, yeah, it's really good, to hear it, you simplified and presented. Just one thing will be, how do you factor in road conditions? Clear roads, snowy roads, icy roads? How is that going to change, the model?
You know, the road conditions, I don't believe are in the legislation at all. I think it would be up to the, reporting officer to determine, what kind of, just like any other traffic violation, the highway patrol or whoever, the responding officer they would be the ones ultimately making that decision. They would be able to take the law and their understanding. I think I don't have a great answer for you, but I think it's a great question. But I think it would probably be up to the officer.
Then what are neighboring states doing in terms of controlling this, or managing this blow? Is it just in Wyoming? Or
So
other states?
as far as I know, Wyoming is the only state that's doing anything like this. We're the only state that even does wind-based closures. There are other states that will put the second part of the message, extreme crosswinds and that sort of stuff, and kind of leave that up to the person. But as far as I know, we are the only state that's really kind of created a more rigorous way of analyzing it. And if you look at where blowovers happen nationwide, you can understand why we're concerned about it. It's a big problem here in Wyoming. We have a lot of trucks and a lot of wind.
I like the part of your presentation where you showed the angles of the wind, and I was wondering, so you said over a certain speed, and you're talking truck speed, the wind direction becomes irrelevant, is that?
The wind direction becomes irrelevant over a certain, once the speed of the truck for these models is always considered 75 miles.
Oh, okay.
But the wind speed, if the wind is sufficient enough, it doesn't need to be a pure cross breeze for it to be over that 25% or that 25% chance of blowing over. So you can imagine if that same wind is coming from a cross breeze, then it's even more significant. But that angle is really for that particular wind speed. And if you look back at that table, you saw that it would start to increase kind of in the middle. And so that it may be a critical one for 48 miles an hour, but if it's a direct cross breeze, maybe that truck needs to be 50,000 pounds. And so that the minimum speed for that particular weather station would actually probably be higher than what my example was. Just if that makes sense.
No, yeah, it's just you got a lot of factors to think about, right? Because you're driving and the wind, but then like if you go faster, the wind angle changes because you're.
Yeah, it's not necessarily the how fast the truck is going, but it's how fast the wind is coming. And that cone of criticality increases, but it also, you can think of the next weight of vehicle, that cone is a little bit smaller. So, eventually you find that cone, that's the maximum weight for that, the maximum minimum weight for that particular stretch. And that's what those tables are doing. And so the way I view it is there's spatial variables, which is like the azimuth of travel and the super elevation. And then there's spatial temporal variables, which is the wind speed and the wind direction. And those vary, across the state. So we've taken the spatial variables that are more or less static temporally, and we've put those in tables. And then we take the temporal variable of the wind speed and direction, feed that to the tables and get those numbers.
Really interesting, pretty cool.
Similarly, I was wondering about the wind gust and how you calculate it back down closer to your steady state. Is that just because like one sudden gust of 70-mile-an-hour wind is not enough to push a truck over? You need more of a steady.
We do consider that for sure. And what's not shown in these and has been incorporated into some of these messages is which one is driving it. So I've added into our messaging is it the wind speed or is it the wind gusts that are driving that minimum weight? And so, we do have some of that information available. It's a simple mathematical formula. If the wind gust is greater than 2/3 of the wind speed, then it's the one driving the minimum weight. If the sustained wind is more than 2/3 of the wind gust, then it's the one driving the weight. So the math is not particularly hard, but conceptually, that's how the model is driven. So we're just reverse engineering.
I just thought it was interesting that based on the table, a 68-mile-an-hour gust would have a weight much lower.
The table was sustained, it's not gust.
Okay.
Cool. So that's where, yeah.
Do trucks blow over when they're going 75 miles an hour? Or do they, you have to figure it out?
As the
more
vehicle-
like ball
As the
climbing
vehicle
or-
speed increases, the likelihood of blowing over also increases. So that's why we chose 75.
Damn.
If they're going slower, the likelihood of blowing over is actually lower.
Lower. Oh, wow. Okay.
So it isn't the case that if you put a spoiler on your truck and went 100 miles an hour, it wouldn't increase the weight? And kind of joking, but kind of like serious.
To decrease the negative pull on the back of the truck. This particular one, you would need a spoiler along the side of your truck.
Well, I mean,
That
like,
makes sense.
but so if your truck, it has an angled profile, the more wind pushing from the front would push it down harder, right? Would increase the weight, or no? I don't.
Potentially, I don't think it's gonna increase it to the level that we need.
So if I'm ever in a semi, don't speed up to 120 if it's really windy.
Like some sort of deployable spoiler. It's basically this direction. Flip it up on the opposite side and pushes, wait, no, that would make it worse.
Okay, so Nick, what's next?
What's next?
Yeah, what's next with?
So, what I talked about, we're developing that portal. So we just had a meeting about this morning. So we're starting to think about what this portal could look like. We need to, right now, these track messages that I showed you, if I can get back to it. So this is live, it's in our development database, but it's pulling live data. We're evaluating that. So we're using right now, those weights are based purely on the wind speed and not the wind direction. So we're evaluating this data against what we're currently doing and seeing if we need to refine our model for that. So we're evaluating this. The next steps is to move this data from our development environment to our production environment so that we can start using that in our production systems and develop a flow chart for our PMC operators to interact with this. So, for example, if they get this increase, they wouldn't decrease it for, let's say, 30 minutes, because we don't want to change these too often. For the the traveling public, it would be too confusing if it was always changing very often. Maybe it's an hour. So develop that flow chart for how often those messages go out. Those are kind of some of the next steps.
Yeah, that's my next question. Like, how do you prevent this sign from flickering? Close or not close, like if I'm trying to like, oh, okay, we're good, and then it's like, and no, it's not good, you gotta, so you're halfway down the road and now you're breaking the law.
Yeah, and that's why we're using the computer with high fidelity, high temporal fidelity, a lot of data, and we're feeding that to humans. So they're the ones that are gonna make that decision. So we have that human buffer, so to speak. So it doesn't go straight to the sign.
Yeah.